Have you ever wondered how our muscles contract? Not just the big, noticeable flex of a bicep or the powerful contraction of a leg muscle propelling us forward in a sprint, but the tiny, microscopic processes that make those movements possible. The answer lies in something called the sliding filament theory. Imagine two proteins, actin and myosin, inside each of our muscle cells. Like two dance partners, they interact in a precise and coordinated way to trigger muscle contraction. Now the dance begins with a nerve signal. This nerve signal is like the music that cues the dancers. Once the nerve signal arrives, something fascinating happens. Calcium ions, which have been patiently waiting for their moment, are released. These calcium ions are like the dancer's permission to begin their routine. Once the calcium ions are released, the myosin filaments bind to the actin filaments. This binding is a crucial step, like a dancer's hand gripping their partners. But this binding isn't possible without energy. That's where ATP, or adenosine triphosphate, comes in. ATP is the energy that powers the binding and subsequent movement of the myosin along the actin filaments. As the myosin walks along the actin filaments, sliding past each other, the sarcomere, the basic unit of muscle contraction, begins to shorten. This shortening is the actual muscle contraction we feel and see. But what happens when the nerve signal stops? How does the muscle know to relax? Again, it's all about the dance. When the nerve signal ceases, the calcium ions are pumped back into storage, like dancers retreating to the wings. With the calcium ions gone, the binding between actin and myosin is released, allowing the muscle to relax. In summary, the sliding filament theory explains muscle contraction through a dance of proteins, actin, and myosin within muscle cells. Triggered by a nerve signal, calcium ions are released, enabling myosin filaments to bind to actin filaments. ATP provides the energy required for this interaction, and as myosin and actin slide past each other, the sarcomere shortens, causing muscle contraction. When the nerve signal ends, calcium ions return to storage, and the binding between actin and myosin breaks, allowing the muscle to relax. So, the next time you flex your bicep or sprint down the street, remember the intricate dance happening on a microscopic level inside your muscles. That's the beauty of the sliding filament theory.